In 1982, archaeologists lifted a wooden ship from the sand beside the Great Pyramid. It was more than 40 meters long and built roughly 45 centuries ago. Its hull contained enormous cedar planks, some stretching more than 20 meters. The pieces fitted together with joints, lashings, and carefully shaped wooden surfaces. But the archaeologists found something that seemed to be missing. There was no surviving technical blueprint explaining how to build the vessel. No numbered construction plan, no table of dimensions, no complete engineering drawing. Yet the finished object was not a canoe improvised from a single tree. It was a complex wooden structure designed to hold its shape on water. Every plank had to meet another plank along a curving, three-dimensional surface. A small error near the bow could become a large distortion farther aft, and the builders could not press a button to calculate the correct shape. They could not open a digital model or order identical factory components. Most of the measurements existed nowhere except inside the construction process itself. So how do you build a ship when the drawing is not on paper? The first mistake is imagining an ancient shipyard as a primitive modern factory. We expect the design to exist first, complete and separate from the material. An engineer specifies every curve, and workers reproduce those instructions exactly. But for much of history, design and construction were not separate activities. The ship emerged from a conversation between wood, tools, memory, and judgment. The builder did not necessarily begin with every dimension already decided. He began with rules, proportions, sequences, reference points, and familiar shapes. Those rules could generate a complete hull without describing every plank beforehand. Think of a recipe known by a baker who rarely weighs ingredients. The recipe is real, even when it has never been written down. Shipbuilding knowledge worked in a similar way, but with much higher consequences. A failed loaf wastes flour. A failed hull can sink people and cargo. So the knowledge had to be reliable, repeatable, and preserved across generations. It was not vague instinct. It was a disciplined, technical tradition. The blueprint was not missing. It was distributed across people, objects, and actions. Before construction began, the builder faced a material that refused to behave uniformly. Wood is not an industrial sheet with identical strength in every direction. It grows with fibers, branches, knots, curves, and internal stresses. Cut across those fibers carelessly, and a strong tree becomes a weak plank. Follow them, and the fibers carry force along the length of the timber. Viking shipbuilders often split timber along its natural grain instead of simply sawing it. That produced lighter planks whose fibers continued through the finished component. Naturally curved branches and trunk sections could become curved structural members. Instead of forcing straight material into every shape, builders selected useful shapes from forests. The forest was not merely a warehouse of wood. It was a catalog of curves. A skilled buyer could inspect a standing tree and imagine its future location. One trunk might become a keel. Another might supply long hull planks. A branching section might contain the exact angle needed for a frame. This reduced cutting, preserved strength, and turned biological growth into structural engineering. The first design decision happened years before the wood reached the shipyard. Modern wooden ships are often imagined as skeletons covered with an outer skin. Frames define the shape first. Planking is then attached over those frames. Many ancient Mediterranean ships were built in almost the opposite order. The outer planking was assembled first, creating much of the hull's shape. The ribs were inserted later, after the shell had already begun defining itself. Archaeologists call this family of techniques shell-first construction. It changes the problem completely because the hull becomes its own growing template. Each new plank is fitted against something that already physically exists. Its edge can be marked directly from the neighboring plank. Remove the plank, trim it, return it, and test the fit again. The process is slower than copying a digital file, but extraordinarily informative. Every contact surface tells the builder where material must be removed. Every gap reveals where the curve is still wrong. The object continuously reports its own errors during construction. The shipyard becomes a full-sized feedback system made from wood. But fitting planks side by side was not enough for a large seagoing hull. They had to resist sliding, twisting, leaking, and separating under changing loads. Mediterranean builders developed rows of mortises cut into neighboring plank edges. Small wooden tenons entered those mortises and aligned the planks together. On many vessels, pegs locked the tenons so the connection could not withdraw. Thousands of these joints could turn separate planks into a continuous shell. The technique appears on Bronze Age wrecks such as the Uluburun vessel. That ship carried copper, tin, glass, ivory, and luxury goods across the Mediterranean. Its builders created a hull strong enough for international trade centuries before Rome. And they did it by repeating one carefully understood joint again and again. This is one secret of ancient complexity. Difficult systems built from familiar operations. The builder did not solve the entire ship as one abstract mathematical object. He solved the next edge, the next joint, and the next changing curve. Local decisions accumulated until they produced a structure larger than any individual. The ship was planned globally by being controlled locally. The Egyptian solution could be stranger still. The vessel buried beside Khufu's pyramid was not assembled like a modern nailed hull. Many planks contained channels through which heavy rope lashings could pass. The ropes pulled the wooden elements together from inside the vessel. Tighten the lashing, and the hull closes. Release it, and parts can separate. Some evidence suggests the design could be dismantled and reassembled when necessary. That would make transport around obstacles or across land more practical. The longest planks were joined with elaborate scarf joints rather than simple cuts. Mortises helped align the timber, while lashings supplied much of the structural tension. The result behaved less like a rigid box and more like a bound wooden system. Flexibility was not automatically a defect. A vessel on water constantly bends as waves support different parts of its length. Too rigid and concentrated stress can break a component. Slight, controlled movement can distribute force through more of the structure. The ship survived not by refusing to move, but by moving without coming apart. Now imagine measuring this structure without a standardized steel tape. Ancient builders still had units, rods, cords, dividers, straight edges, and marked references. But exact numerical dimensions were only one possible way to preserve shape. A physical template can store a curve more directly than a written description. Place it against timber, mark the edge, and the curve has been copied. A knotted rope can preserve intervals without requiring every worker to read numbers. Dividers can transfer one distance repeatedly from one component to another. A master frame can establish a crucial section of the hull. Other shapes can then be generated by controlled changes from that reference. The information is not written as coordinates. It is embodied in the tool. This is why losing an object can mean losing part of a technical language. A future archaeologist may find the ship, but not the temporary molds used to shape it. He may find tools, but not the gestures that made those tools precise. He may find measurements, but not the sequence that gave them meaning. The most important document may have disappeared because it was a performance. At the center of this system stood the master shipwright. He was not simply the strongest carpenter or the person holding the largest hammer. His value lay in recognizing relationships that apprentices could not yet see. He knew when a plank's curve would create trouble 5 meters farther along. He could sight along the hull and detect a distortion before measuring it. He knew how wet timber would bend, dry, shrink, and change after launch. He knew which imperfection was harmless and which would grow under stress. Much of this judgment came from years of observing consequences. A vessel returned leaking, another handled badly, a third survived a storm. Every success and failure updated the unwritten model inside the workshop. This knowledge was empirical, but empirical does not mean accidental. It means conclusions were tested against reality instead of only against theory. The ocean was an unforgiving examiner. Bad traditions disappeared when their ships repeatedly failed. Working traditions survived because generations kept testing them against wind and water. But memory inside one expert is fragile. When he dies, everything that was never transferred can vanish with him. Traditional workshops solved this through long apprenticeship. The apprentice began with simple jobs, carrying timber, sharpening tools, holding lines. At first, he copied movements without understanding the complete system. Then he learned why one plank was accepted and another rejected. He learned where to stand when judging a curve. He learned how a correct tool stroke sounded and felt. He learned when a rope was tight enough without breaking the timber. The workshop copied knowledge by copying skilled attention. This required time because judgment cannot be transferred in one explanation. You can describe balance, but balancing still requires repeated physical correction. You can name a fair curve, but the eye must learn to recognize one. The body becomes part of the measuring instrument. Apprenticeship was not informal education. It was high-capacity technical storage. More than 3,000 years after Khufu, Scandinavian builders used another powerful sequence. They began with the keel and the curved stems at bow and stern. Then they added long rows of overlapping planks called strakes. Each plank overlapped the one below it and was fastened along the seam. The growing shell curved upward until the recognizable long ship form appeared. Frames were fitted inside after much of the outer shape already existed. The overlapping planks produced a hull that was light, strong, and slightly flexible. That mattered because long ships had to cross open water and enter shallow rivers. A deep, heavy vessel would lose the very mobility that made it useful. The construction method was therefore inseparable from the ship's intended behavior. Form was not selected because it looked impressive. It emerged from timber, water depth, sail forces, cargo, oars, and experience. Change one requirement, and the proportions of the vessel changed with it. Traditional builders produced families of ships rather than one universal design. The method behaved like an adaptable algorithm executed by human hands. A ship does not need arbitrary dimensions. It needs dimensions related to one another. Length influences speed, capacity, turning, structural stress, and the number of rowers. Width influences stability, cargo space, drag, and how much sail the hull tolerates. Depth affects freeboard, internal volume, and the danger of taking water aboard. These relationships can be managed through proportions before they are expressed as equations. A builder might derive one dimension from another using a familiar rule. The actual numbers could change while the relationship remained recognizable. This allowed a known design family to be enlarged, reduced, or modified. Not every scaling attempt would work perfectly because forces do not scale equally. That is where accumulated experience corrected the simplicity of the rule. A proportion suggested the first answer. Material behavior refined it. The complete design lived between a remembered ratio and a physical test. This is less precise than modern naval architecture and calculation, but within familiar materials and vessel types, it could be remarkably dependable. The system was narrow, practical, and refined by centuries of costly feedback. Now picture a shipyard before sunrise, while the hull is still incomplete. The master walks beneath the planking with two senior builders. One section near the bow has begun to twist outward. No surviving manual tells them exactly what correction to make. They stretch a line, sight along the edge, and press the timber inward. One proposes trimming the plank. Another warns that too much wood will weaken it. The master orders the timber dampened and held overnight under controlled pressure. By morning, the curve has shifted without sacrificing the plank's strongest fibers. That decision may never appear in any historical text, yet hundreds of decisions like it determined whether the ship would live or die. History preserves kings, battles, destinations, and cargo. It rarely preserves the correction made quietly before breakfast. But engineering often succeeds through exactly these invisible interventions. The monument is famous. The judgment that saved it disappears. What survives is the result, stripped of the intelligence that produced it. You might think the builders simply copied the previous ship, but no two trees supplied perfectly identical timber. No two cargoes placed weight in exactly the same way. A longer route, heavier mast, or wider beam changed the problem. So tradition had to preserve principles, not merely frozen dimensions. A competent master could recognize which features were essential and which were adjustable. The keel line might be altered while a familiar joining sequence remained. Plank thickness might change while the logic of overlapping edges remained. A cargo vessel could grow wider while retaining the workshop's construction grammar. The tradition was therefore neither rigid repetition nor free improvisation. It was controlled variation inside a tested system. That is the same fundamental problem faced by modern engineering standards. Preserve what prevents failure while allowing adaptation to a new situation. Ancient builders encoded that balance in craft instead of software. Their algorithm ran through eyes, hands, templates, ropes, and repeated corrections. But the romantic image of one genius builder is also misleading. A large ship required timber cutters, transporters, rope makers, smiths, and carpenters. It required food, wages or rations, storage, schedules, and access to suitable trees. It required authority capable of organizing labor over months or years. The ship was therefore a technological object and an organizational achievement. A perfect master without seasoned timber could build nothing. Excellent carpenters without rope, food, or time could not finish the hull, and a wealthy ruler without craft knowledge could waste enormous resources. The hidden machine was the entire network that delivered coordinated expertise. The vessel floated because the society behind it functioned before launch. This explains why a sophisticated craft can disappear surprisingly quickly. You do not need to erase every tool or destroy every surviving vessel. You only need to interrupt the chain that produces competent masters. Remove demand, scatter the workforce, or eliminate access to critical materials. Within one generation, rare judgment becomes rarer. Within two, it becomes reconstruction. The tools may look simple, encouraging outsiders to underestimate the lost knowledge. An axe does not explain which tree to choose. A template does not explain when its curve should be modified. A wreck does not explain the corrections made before it touched water. Material evidence preserves the nouns of technology better than the verbs. That gap creates the illusion that ancient builders possessed mysterious secrets. Usually, the secret was not one hidden trick. It was thousands of ordinary decisions performed in the correct order. Remove the order, and the surviving pieces stop explaining themselves. The mystery appears only after the workflow has vanished. The next time you see an ancient hull in a museum, look past the timber. Imagine the missing forest, selected tree by tree. Imagine the ropes tightening, the tools striking, and the planks being tested repeatedly. Imagine an apprentice watching a master reject a curve almost everyone else accepted. Imagine the hull sliding into water before anyone could be certain it would survive. Then imagine it disappearing beyond the horizon, carrying people who trusted that knowledge. They were not trusting a piece of paper. They were trusting centuries of decisions stored inside the way the ship was built. The blueprint was there the entire time. It was not under the shipbuilder's hand. It was inside it.